Hello everybody, Tortoise here from KTaNE, and today we're doing a special video talking binary system introduction. In KTaNE there's a lot of places, lot of modules where you need a binary system, so I decided to kinda make a video since the repository isn't working. So, what even are the digit systems? Well, the binary means that there are only two digits in the system, 0 and 1. The decimal means that there are 10 digits from 0 to 9. There can be ternary system with 0, 1 and 2 and so on and so on. Even hexadecimal which has 16 digits, 0 to 9 and then alpha to foxtrot. So that's like the main thing of the name of the systems. Also, we're using the base of the system, which is the number of digits in the system. So in binary we are using the power of 2s, in decimals we are using power of 10s, in hexadecimal we are using powers of 16 and so on. I've written down an example of a number written in decimal system, 9872, and we can factor this number out to sum of products of the digit in the corresponding position and the power of the base corresponding, of course, to the position as well. Therefore, we can write this number as 9 times 10 to the power of 3 plus 8 times to the power of times 10 to the power of 2 plus 7 times 10 to the power of 1 plus 2 times 10 to the power of 0. Because 10 is the base, since we are in the decimal system, and all these digits, 9, 8, 7, and 2, are from the decimal system. That's kind of the main thing. If you don't know what the power is, I would recommend to check out the video or just to have a look at what that means. Essentially, just a reminder, 10 to the power of 3 means there are 3 tens that are multiplying with each other. Therefore, this is 10 to the power of 3. In terms of 10, that also means that there's a 1 and then 3 zeros, because that's the same thing. In other systems, like let's say ternary, 3 to the power of 5 means there are 5 threes that are multiplying with each other. Therefore, we would get 243. And so on and so on. So this is not as easy as in decimal system, since it's not just about sorry about the noise, about adding zeros to the end. Not real adding, but writing them after the one and the other zeros. Okay, so that's a quick reminder of powers. And now, in this video, I would like to introduce you how to convert the decimal number into binary and binary into decimal. Both ways, because that's what you need in KTaNE, and this can help you a bit. So, if you just write a number, another example, if you just write a number 101, this doesn't have to be always 101, since that would be the decimal representation of the number, if this is in the decimal. However, if this is a binary number, then the decimal representation of that number is 5. Or ternary, then it would be 30. Or if this is hexadecimal, then the decimal value is 257. Therefore, one number doesn't have to really be the value you're expecting. You have to also use the system that the value is written in. So, that's also leads us in a difference between a digit, which is just a symbol, really, that is used in a position of some power, and the number itself. 1 is a symbol, therefore then it's a digit, and one-digit number is a 1. So one-digit number is a 1, but this is a symbol 1. The difference between these two are in context. Yeah, that's kind of it. Okay, so let's go. Let's write down a binary number example. Let's start with this number. Okay, we have this number. I'll mark a little 2 here, just to note that this is the binary number and not really 1011. So this is binary number 1011. And now we would love to write down the decimal representation of that number. So how would we even do that? Well, the trick is very simple. We just have to factor that number out like we did in the decimal system above. However, now since we are in the binary system, the base is 2, not 10, but 2, because we have 2 digits, 0 and 1. So we would get something like 1 times 2 to the some power plus 0 times 2 to the some power plus 1 times 2 to the some power plus 1 times 2. And since this is the last digit, the least significant digit, the digit most to the right, this is the power of 0. Then this is incrementing by 1, so 2. This is this is 2, but power of 1. This is the power of 2 and power of 3. So we just count from 0 always, 0, 1, 2, 3, and so on. And now we can just simply... this is, by the way, the decimal representation already. This is decimal, not binary anymore, since there are some 2's. And 2 doesn't really exist in binary system. It's just used as the value. So now we can just simply calculate this. Every number except 0 itself to the power of 0 is 1. So these, the last significant digit, always represents the number of units. So there's 1 unit. In this number above, there are 2 units. Then we would have 7 tens, 8 hundreds, and 9 thousands. In this number, we don't have really tens, hundreds, and thousands. We have this is 1, so this is units. 2 to the power of 1 is just a 2. So these are 2's, not really tens, but 2's. These are 4's, because 2 times 2 is 4. So these are 4's, not hundreds. And these are 8's, because 2 to the power of 3 is 2 times 2 times 2, which is 8. So that's what we get. 1 units, 2's, 4's, and 8's. And since in binary you have only 2 digits, therefore it's much more simple than in other systems, because we don't have to use like the digit as the representation of how many units or 2's or 3's, I don't know, there are, but we just have we can just ask, are there any? And if there are, we can answer yes, and that means in binary that means there's 1, because there can be any other non-zero amount than 1. So we just sum, essentially we just sum the positions that are present or that are not 0. So we have 8, 1 times 8 is 8, plus not 4 is 0, so we ignore that. Then there's 2, so we add 2, and then we add 1, because the last power is 1. So we get 8 plus 2 plus 1, which is just 11 in tenth. So in decimal. So we have 11. So this number, 1011 in binary, means 11 in decimal. And that's how I do it. It's as simple as that. I have some representations here. Oh, sorry, here first. We have some conversions. 0 is just a 0 in decimal. This is from Wikipedia, by the way. And you can see 1 is 1, but 10 in binary means 2 plus 0, 1, so just 2, so it's a 2. This is 2 plus 1, so 3. This is 4 and nothing else. This is 4 plus 1, 4 plus 2, 4 plus 2 plus 1, 7. Then 8 and nothing else, and so on and so on and so on until 15. And you can kind of see the pattern here. Then 16 would look like 1 and 4 zeros, so 10,000 in that cell, but let's just call it 1, 0, 0, 0, 0. And so on and so on. So this is this conversion is very simple, I would say. When you get used to it, this direction is not as tricky as the other one. So let's how do you convert the other way? Well, I have some powers of 2 here written. We have to do the same thing, however, the other way, which means let's just write an example. For example, let's say we want to convert the number 25, which is in decimal, and we want to put it in binary. How do we do that? Well, we have to ask ourselves, what's the highest power of 2 that can be subtracted from the number 25 to yield positive number, or at least not negative. Yeah. Well, so it can be 0 as well. So what's the highest power of 2? Well, I have some powers of 2 here. 1. Well, yes. 1 suffice. 2. Well, okay. Yes, it can be subtracted. 4. Yes. 8. Yes. 16. 25 minus 16 is still 9. 32. 25 minus 32 is negative 7. So 32 is too much. So 16 is our answer here. So we have to subtract 16. So the highest power is 16, which is 2 to the power 4. 4 2's have to be multiplying each other to yield 16. So this is 2 to the power 4. Now, what is left? Well, what did we did 16, so we are left with 9, because 16 is already here. So 9 is the remainder, and now we have to do the same thing again. So 16, no, 9 minus 16 is too much. So let's go just 1 below. 8. 9 minus 8. Yes, that's positive, or at least not negative. It's a 1. So 9 minus 8 is a 1. And we use this 8. So this is 2 to the power 3, or 2 cubed. Now 1. Well, 4 is too large, 2 is too large. 1 is exact amount we need, because 1 minus 1 is a 0. When you get the 0, that means we are done. So we just add 1, which is 2 to the power of 0. I can also write this down like 16 plus 8 plus 1. So it's more clear what's happening here. And that's kind of it. But since we want to do the number in binary, all of these are still decimals, we have to look at the powers of 2's and write 1's and 2's. There will be always that many digits as the highest power plus 1. So we have highest power is 4, therefore we need 5 digits, because 4 plus 1 is 5. So 5 digits. First digit is always a 1, otherwise it would be called leading zeros, the same like 25 is the same in decimal as 0.25 and so on, and 0.025. This is still the same number, so it always starts with 1 if you aren't told to, I don't know, write down the leading zeros as well. So the number is always 4 digit. In that case, it would be 4 zeros. This would be 0001, 001, and so on. Always like that, and that would be all 4 digits. But we can ignore that in this case. Then this is the power of 4. Then we go 1 down, which is 3. Yeah, it is present, so we put 1. Then power of 2, it is not present, so we write down 0. Power of 1, not present, 0. Power of 0, 1. Nice. If the by the way, if the original number is odd, then the binary number always ends with a 1. If it's even, then it ends with a 0, because all the other powers of 2 are even. So this would be our binary representation of the number 25, 11001. And that's kind of it. I can show you one more trick to do it faster, but in KTaNE this usually suffices. So the trick is, let's say we want to do number 73. This is kind of a big number, and you may not remember that the highest power is to the power of 6, which is 64. So you can just try to divide this by 2. And if you divide it by 2, we get, it's not always divisible, so we have 36 and a half. If you do that in your head or calculator or anything. So we ignore the half and we just write down 36, and the remainder is 1. So we divide it with a remainder. Then we divide 36, which yields 18, without a remainder, so 0. And then we do this. So this is 0 again. This is just a 4 with a remainder. This is 2 without remainder. This is 1 without remainder. And the last digit, always 1 divided by 2, is 0, remainder of 1. When we get to 0, we are done. And now we just have to read this number from the bottom to top. From the bottom to top is the most important thing. How to remember this? Well, the last digit is always a 1. Therefore, the first digit, the most significant digit, is always a 1 as well. That's why you need to start from the bottom. Like, just to remember it. It's not a reason, but just remember it. Also, the first digit is a 1 in case if this is odd, and if this is even, then this will be a 0. So that's also a thing to remember. And now we can just write down that 73 in decimal means 100 from bottom to top, 1001 in binary. 100101 in binary. We can also try it the other way. This is 1 plus 2, 4, 8, 16, 32, 64. I'm just multiplying by 2 every time I move 1 to the left, and this yields 73. So indeed, this number means 73 in decimal. Okay, that's kind of the fast tutorial I decided to make. If you had any concerns, questions, anything, just write it down in the comment section below. If you need also an introduction to the hexadecimal system, for example, or anything concerning maths, you can just ask. And if you like this video, please leave a like and subscribe to the channel if you liked it. Thank you for watching, and see you in the next tutorial. Bye bye.